Okay. So it's our last seminar of the quarter. We're very happy to have Jan Albert from Princeton, and he'll tell us about a recent paper on confining strings. Go ahead.
Thank you very much. Thanks for coming and thank you for the invitation. It's a pleasure to tell you about my work. I didn't realize it was the last podcast semester, so it's I don't know if the bar is very high or not, but I'll try to do my best. So yeah, I'm telling you about this paper that we put out earlier at the beginning of the year together with Chandra Hombridge on trying to learn what asymptotic freedom can tell us about confining strings. So just before I write down anything, some opening words. About confining strings. So we were interested in confining H theories. For a long time, there's this expectation that there should be some sort of dual string description of confining H theory. And that's what we mean by confining strings. It's not we're very far from having, in many cases, our cases closer to the real world. We're very far from having the whole worldsheet action for these confining strings. And what we're trying to do is trying to make some progress and understand various, well, as much as we can of these confining strings. So a direction that's been proven very fruitful is to look at the low energy limit of these fugitive strings, where we have some effective description. And there's been a lot of recent progress in that limit, the limit of low energies. And we have some effective string theory description that works very well. The problem is that in that description sort of forgets many of the details of the underlying theory, and then we need to work very hard to recover those. So what we'll be doing is we're trying to so for example, if your underlying theory were asymptotically free, you might, well, in principle, like the low energy FT doesn't know anything about that. I mean, it's encoded in the various coefficients of the theory, but in a very convoluted way. So what we tried to do with Alexander, the question that we posed was, what does asymptotic freedom teach us about these confining strings? Now, naturally, this will be a question about high energies of the string. That's where asymptotic freedom kicks in, rather than low energy. And it still remains open how to connect one to the other. But it's still interesting to look at different limits of this fugitive string dual and see what we learn. Okay, so to be concrete, the theory that we're working with will be theory on nails. That is going to be true. So that's why it's close to our real world, but without dynamical matter. And there's a sharp definition of confinement and deconfinement in terms of a long-form symmetry. And we'll be working in space-time v equal 3 and 4 dimensions simultaneously. We're doing 3 and 4 because that's where there's the string has some transverse directions today, 1 or 2 transverse directions. And in these dimensions, the theory is still UV free, so asymptotically free. And then we're overtaking the limit of n going to infinity in the tooth sense. So there's a tooth coupling. That's G minus squared n, which we keep order 1. So okay, so it's not to say that this is constant. In fact, it runs with energy, constant mu, and the statement of asymptotic freedom is that this tooth coupling goes to 0 as the scale of the process goes to infinity. Okay, so we have a theory that so this theory is free at high energies, and then we can trust the we can use perturbation theory in terms of quarks and gluons. But then at lower energies, this becomes fractal, we can have this. The idea is to use this asymptotic freedom, so we'll do some perturbative computation in the UV and see what that teaches us about the confining string. So okay, so this is the theory we're interested in, and in particular, the large n limit is also the limit where this picture of a putative string dual is cleanest, and this comes about in a tooth large n expansion. So if you look at whatever process you're interested in, there's some expansion Feynman diagrams, which has some, according to their topology, which arranges in orders of 1 over n. So we have, for example, a sphere contribution, and then we have higher genera, so on and so forth, which come with different powers of 1 over n squared in this case. Okay, so this expansion, just I'm assuming most people are familiar with this here, and this expansion of 1 over n looks very similar looks and smells like the string theory, like a higher genus expansion of string theory, where we have a string coupling, which is proportional to 1 over n. So we expect that H theories and log gen are dual to some string theory. Mostly, this is one of the main motivations for that. Okay, so good. In the confining phase, there is a very clear cartoon for what these strings might be, and it's the following. So we have some quarks and gluons, but quarks and gluons are not the asymptotic states that we see in our theory. Instead, they're confined and they're attached by these confining strings. So the picture that you can have, which is seen very plainly in the lattice, is one where a quark, which in principle has a bunch of color flux lines coming out. This in the confined phase, all these lines are collimated into some small tube here, which is the flux tube. And this is that provides a sort of classical picture of what this confining string might be. It's just all these flux tubes collimated into some thin tube, which can oscillate.
So I thought you have no matter.
But that, yeah, so this matter for me, the huge point. So this, in my case, in angles, this will be probes. So there are nails on the diaper where my string can attach. If I were to add dynamical matter, then this would be the message that will move about. So I will still have open strings. It's just that the boundaries are probes that I control, and I can decide where I place them. They're infinitely heavy quarks if you wish.
With background charges.
So the string theory, you don't have brains.
I don't have, sorry?
You don't have brains.
Yeah, well,
Dynamical brains.
yeah, that's right. So these are like boundary, it's a classical brains where I have some boundary conditions where I can attach my string. That's right. So yeah, so of course this picture is using QCD where the charges are dynamical, but I can still have these endpoints. Yeah. So right. So the question ideally eventually would like to do is understand the dynamics of this string and study the various excitations of these mesons or probe mesons here, and also the closed string states, which would be some closed flux tube, which also oscillates, and this would be give you the spectrum of blue balls in this species. Okay, so these are the confined states, and the idea is that eventually, once you understand the full world-shape theory, if such a theory exists, then you can quantize it and obtain the spectrum of pure dynamics and confined phase from this world-shape item. Okay. Now, as I was saying before, we're very far from in this theory from having a full world-shape description. In D equals 2, there's a lot of recent progress, and not so recent. But in D equals 3 and 4, we're still very far from having this world-shape description. So what it proves useful is to take various limits. In particular, there's the limit of low energies, where we have low energies. We have, I'll discuss this in more detail, we have an effective field theory, or an effective string theory. And the limit that we're interested in is the limit of high energies, which is where we expect asymptotic freedom to kick in and tell us something about this theory. But so this expectation has been clear for a long time, but the question is, how do you find a good observable which is sharply controlled by perturbative computation? And that's the main topic that I'll discuss from the talk, and then we'll see what we learn from here. Okay, so before I start, there's a brief outline of these points. I'll start with a quick review of what's known on low energy, so that's the more canonical limit that people study. Then I'll discuss some observables there and why they don't fit the bill to go all the way to high energies. And we'll discuss a different observable, which is not that different. It's actually used in all the time. And then we'll see what we learn from matching to perturbative computation, first on the string spectrum, and then on worldsheet dynamics, and by which I mean some scattering processes on the worldsheet of the fluxes. Any questions before we start? Great. So, okay. So let me say a few words about this low energy line. So low energy. So let's see. Low energy. So the low energy limit comes about when we have a very long string. So for example, if I take my probe cards and I pull them very far apart, and if this length is much higher than some scale of the so my theory has some scale which is given in terms of G mills or lines of QCD in T equals 4 or find the young mills in this case. So if this string is much larger than the intrinsic scale of the process, then I can integrate out all the high energy modes of my string theory, my worksheet action, and then only discuss the theory in terms of the low-lying states and theory. So what are these? These are just Goldstone bosons that come from the spontaneous breaking of translations orthogonal to the string worksheet. So we have a very long string placed in spacetime, has some orthogonal directions and some longitudinal directions, and this xi signal which are the emerging coordinates of the string, become the transverse ones to the worldsheet become some Goldstone bosons, and this continuous breaking of translations across the orthogonal to the worldsheet. And then so these become some massless Goldstone bosons on the worldsheet of the string. And then all we need to do is write down some effective field theory that captures the interactions of these Goldstones. Okay, so this is just follows the usual rules of effective field theory, and you just write the most general action that's compatible with the symmetries of the problem. In this case, it's controlled by Poincare invariance of the spacetime, and we have the effective string theory action given as follows: minus integral on the worldsheet of the following. So it starts with the usual non-Goodwell action, which is the one that we know and love from string theory textbooks, dx, and it comes with some scale, 1 over ls squared, which is related to the scale of the underlying theory, G is, in some non-perturbative way. So it's just the intrinsic scale of the theory, and it's the string length or the string tension. And this would be, so if we stop here, this would be the usual string theory that we know a lot, which only works in critical dimensions of equals 26. But here we don't see it as the full theory, we just see it as the first term in an effective Lagrangian of the line energies. Then you need to keep going and add all the irrelevant operators to it, so higher dimensional operators. We have, for example, the first one that's non-trivial. It's the extrinsic curvature to the 4. So this is essentially some double derivative of x to the 4 in a covariant way, and so on and so forth. And it gets multiplied with the Wilson coefficient, which is not fixed by effective field theory. Yeah, and then it keeps going. There's an infinite set of higher derivative interactions. Okay, so this, I want to emphasize that this is an effective action that works for any theory of strings. So any theory where you have long effective strings and at low energies, they'll be described by this action, and the distinction will be encoded in this set of Wilson coefficients. So this is just a way to parameterize our ignorance of the interlaying theory. And then the question becomes, so sure, we can parameterize it in this way, but now how do we fit this? These coefficients, what do we need with these? So then what people do is they look at particular observables of the theory, such that at low energies they can be described by this effective action, and then they match.
Why do I need so many derivatives for the leading correction?
So you can,
Like, I thought number goes to as long as I have a derivatively coupled scalar, that's not enough. Like, why can't I have del x to the 4?
del x to the 4. So this. So you need to be compatible. So yeah, there's actually a covariant derivative, one of them, and the other is. So you need to be compatible with Poincare invariance, and the first one you could have is R, so just like the curvature, the stellar curvature. But this one is a topological invariance. It doesn't factor. It just. But this one's the first that has non-trivial dynamic of Goldstone, but has some non-trivial interactions. I haven't, yeah, and yeah, I mean here if you expand, this is a bit like the chiral Lagrangian, that there's some spontaneously broken symmetry, and it means that you actually are not just expanding by derivatives. So if you expand this thing, you'll actually have many powers of the axis, right? But the point is that they need to arrange into something that's invariant under the spontaneously broken symmetry. In this case, Poincare invariance of the both. And that's why we need to write curvature invariance. It's just list the various ones we have, and the first non-trivial one is the non-trivial step to classify this. And this is in D equals 3, where there's only one. In D equals 4, there's actually 2. There's alpha and beta coefficients. So I'm writing D equals 3 for simplicity.
Can I ask a question?
Mhm.
Maybe it's very naive, but in Yang-Mills, I would say there are 3 scales. One is lambda QCD, one is the length of the string, and the other one is like the size of the oscillations.
Mhm.
Which one should be small for this to be, like, should the length be smaller than lambda QCD, but the oscillations can be whatever? Or
It's both. So it needs to be close to the ground state. So it's an expansion of the area. So you want the area to be so yeah. So for example, so say you're looking at a string and then you're doing some thermal cycle, so that you can consider more or less excited states depending on the radius of this thermal cycle. What you want is the full area of this cylinder to be smaller than G angles squared, or so. Yeah. So you want both. You want low line excitation, so excitation energy states that are below the scale from
so the length
QCD.
times the oscillation has to be smaller than lambda QCD squared,
Yeah.
basically.
Yeah. So that the units match up. Yeah. So it's only a low, so this is, so when I'm saying it's a long string, I just mean, the long string, I want a worksheet that has a very large area. That's the best statement. Thanks.
And maybe something else. So
Mhm.
if we have a symmetry that is spontaneously broken, like the translation here, that gives you this mode, how do we know that there are no other massless modes that do not come from a broken symmetry?
Right, I mean, then it's essentially, and it's, I guess, to a certain point, it's an assumption that, yeah, okay. So if there's lattice evidence, you write this down and you compare, it works pretty well, so that we don't expect it, and in fact, in equals 4, there is a light scalar, that's called the axiom, the worksheet axiom, which was seen precisely by that, you're assuming that there's no such, it's not light, well, it's light enough that you see it, I mean, it's not massless, but it's, yes.
Very close to the contour.
Okay, fair, yeah. So it's not like that big.
It's lambda QCD-ish, it's just an accident that it's kinematically stable.
I see, okay. Yeah, that's fine. But,
It's not parametrically like relative to the blue ball mass from lambda QCD.
yes, it's just that it's ortholine. But, yeah, so very low energy is this is what it is, and it's given by the various symmetries. So we expect that nothing else is protected if there's no symmetry, so it should be in some mass. That's the usual happen. Yes.
In this effective picture, how should I think about conformal invariance of the worksheets?
It's not conformal invariant, yeah, so so usually what you do is you go to, so this and then we go to frame, so you just have this, usually, go to the different frames instead of doing, you go to the polygon formalism, then you fix the metric, and then you have a simple form theory. Here you can't do that, because so we're working directly with number goes, and then you have explicitly some scale. And yeah, so it's not, Polchinski and Salinger worked out how to do the same expansion in the polygon gauge, but you still have some scale in the effective field view. So this will be to be it's still a diffeomorphism there in theory, but it's not. So any more questions? Okay. So good. So then let me go back to this. We have this effective action. We need to look at various some observables that can be computed with this and see what people do. So the main observable that people look at is the ground state energy of a winding string. So ground state energy. So we put the theory in S1 with some radius r or length r times RD minus 1. And then in the non-contractible cycle, we wrap a string here. So we look at the winding one sector, which you can do because it's protected by the one-form symmetry. So you're looking at the charge like flux one sector. So this is the radius r, and that means that if the string is forced to have some length r, it cannot break because we don't have dynamical charges. And then that means that if r is large enough, I'll be forcing the string to be larger. So with that, I take when r is much larger than ls, and also the energy is lower than 1 over ls, then I can use the effective string theory description. And in particular for the ground state, I can just compute the ground state energy of this winding string with the effective action. So what people do is they compute the ground state energy is 0 as a function of r of the function of the radius for this ground state of the string. And you start here and you find that it's a linear term. So it's asymptotically, it looks linear. The energy is proportional to the tension 1 over ls squared times r. That's what you expect for a confining string. And that's basically by definition, because the leading term is just the area of the worldsheet. But then there's corrections on top of that, which come in terms of, so there's some universal corrections that come from the number of piece, but then eventually there's a non-universal corrections that come with this coefficient. So it's this thing. I think the first one is r to the 7. This is again equals to 3. It depends on the dimension you're doing, but it's divided. So there's some corrections that deviate from the linear energy or potential, and then these deviations are precisely what people fit. So you can do this expansion and fit it to lattice data, and this extracts for you the various coefficients gamma 3, gamma 5, and so on and so forth. So there's one way that people use this effective action to extract the Wilson coefficients from lattice data. Okay, so this is one way of being observable that people discuss. Another one is somewhat different, and it's the worksheet as matrix. So we'll discuss that one. So this is energy. So this is the S matrix not of globals in spacetime. This is an S matrix on the worksheet. So we have a very long string, infinitely long, and then we consider two little ripples on the string. That would be the transverse constants like Xi and X2, and then we shoot them in with some momentum, intervallic momentum P. Then they come in on the string, they collide, and then they go back out again. And we look at the 2 S matrix of Goldstone bosons. So this is the S matrix, J, L, as a function of little s, which is the minus limit variable. So this is 2D scattering, so there's no S and T, there's only S, there's no angle, but you can still look at this this process. So now this is defined all energies S, but when S is much smaller, S is much smaller than 1 over LS, so a low energy, 1 over S squared. That's where you can use the effective string theory expansion that I discussed. And if d equals to 3, I'll show most of my results that I'll actually write down will be for d equals to 3 because they are just simpler. The reason is that these i's run from 1 to d minus 2, if they are the transverse nodes of the string. And yeah, in d equals to 3, there's only just 1, so I can basically delete the indices, just simpler. So then the S matrix of the S matrix is like follows. It's a pure phase. It's S of I S Lx squared divided by 4 plus 10 of 3 S cubed plus a plus. So there's a low momentum expansion as usually in effective field theory, which comes with various Wilson coefficients of the effective action. Yes, please.
Does the boundary condition matter here, or should I think of this is so large that the Goldstone boson never sees the boundary?
That's right. So that's a very good point. This is I mean considering an infinitely long string, but soon enough we're actually going to consider a boundary, and I'll consider scattering events of the up against the boundary. So this
That doesn't consider.
what was that?
That the expansion of the S matrix doesn't consider.
No. So this would be some collision in the bulk of the string, and the string is much larger than the initial separation of the string. Yeah. But I mean, formally it's infinity. You think of a Fock space coming from plus infinity and minus infinity. But yeah, it's you think of the string being longer than that. Yeah. But we'll put a boundary very soon. Okay. So at low energies we have this effective action, and then this scattering amplitude, which also captures the same coefficient here. And then what people have done recently, or not so recently, is to use the fact that this S matrix has to be unitary and so on. So absolute value of S, and the real axis has to be bounded by 1 and so on. And this S matrix bootstrap to put universal bounds in these coefficients. Just for illustration, for example, gamma 3 has to be greater or equal to minus 1 over 7, 6, 8, whereas that LS1 is in units where this is dimensionless. Anyway, so the whole point is that we have these two observables or some more, but we have the constant energy and the S matrix, and at low energies they're great, we can extend them very well. And then we have some bootstrap bounds that are universal and also some lattice determinations of these coefficients. I would say that the low energy limit of these strings is quite under control. So the limit that we'll be interested in is the complete opposite. It is the limit where energies are much larger than 1 over LS.
So before you go, can I ask
Yes.
a question? So this worldsheet theory is not integrable, no? So like you can have in principle particle production and all this stuff. You just don't consider it.
Yeah, that's a great question. So it just so happens to have accidental integrability at low energy. So there's just a pure phase. But soon enough, in d equals 3, when you reach S to the 8, then you have particle production stuff kicking in. So it just it so happens that the Hamburger action gives in d equals 3 an integral as matrix, but then by the time the K4 term kicks in, then you start having particle production. So yeah, and this has been very useful in the program by Dubovsky and company, where they're using integrability at low energy, so they can do games like thermodynamic transits and so on, which is suited for integrability, and apply it to these flux too. But I should say that the gamma 3s that have been measured from lattice are incompatible with full integrability of the worldsheet. So no, and the theory is going to be non-integrable, which just so happens at a low energy, up to certain order phase.
So what's this extra symmetry that makes it integral?
This extra symmetry. Yeah, I'm not sure. As far as I can tell, it's just an accident, but I don't know. Okay, any more questions? Okay. So we're looking at this upper limit, which is the limit where we go to very high energies, and we want to use some perturbative computation from leveraging asymptotic freedom of the underlying theory. Now, this is so people have thought about this for a while. Like it's being clear that the high energies of the string should be controlled by asymptotic freedom, but the question is how to do this sharply. And there's two main obstructions, as far as I can tell. The first one is that when we do computations with QC de Lagrangian, they're bulk or Yang-Mills Lagrangian, they're bulk computations. In terms of coordinating gluons, it's for some observable in the bulk, so RD or RD minus 1 times 1, whatever you like. But they never have to do with the string, right? The string is something that's very strongly coupled, so we don't know exactly how to we cannot just do some computations. So we need some. If we want to say something from asymptotic freedom for the worldsheet, we need some clean map between some worldsheet observable and some bulk observable that we can compute perturbatively. And then the other issue is that we need some smooth limit to the UV, which doesn't trigger any phase transition. For example, if we're trying to discuss confining strings that are in the confined phase of the Yang-Mills theory, we don't want to take some limit to the high energies that goes to the deconfined phase, where some other string theory description may apply. We want to, so that with this maximally controlled, we want to remain in the same phase as we phase. Okay, so now we can the question sharply is what observable do you find of this dual string theory that is controlled nicely at high energies by asymptotic freedom? The first thing you can do is try these two observables that I explained, and they don't quite work for the following reasons. So we come here, we know, so as R is much larger than LS, we had the effective string theory. Now what we want is R much smaller than LS. So we want to be in this region over here. And the question is, can we do perturbative computation here? The answer is yes, but the issue is that if you look at lattice plots, for example, and you start following this line down, you see that it hits 0 at some non-trivial, so non-zero value of R, RH, and then after this, it shoots into the confidant. So this is the Hagedorn radius from a string theory perspective, and it's where the ground state of the closed string ground state becomes tachyonic. So your string, so you're basically doing some expansion on around your ground state, but your ground state becomes unstable. So you're doing expansions around the wrong phase and triggers phase transition. Yeah, you can also look at this by thinking of this direction as time, and then so R is basically 1 over temperature, and then this at least at large M becomes a deconfinement transition. So you're going to high enough temperatures, and the theory deconfines. So here you'll have some description in terms of some glowing plasma, which sure you can still do perturbatively, but there's no guarantee that it still should be described by the same confining string theory that we were using down here. Okay, so that's the main expression. There's no smooth on these observables. There's no smooth limit between the IR to the UV. So what about this one? Let's discuss.
Yeah, I have a question. This is an old problem. There's this trick of stabilizing the theory on a circle from preventing it from undergoing a deconfinement transition by putting Wilson lines.
Sorry. Okay. So I mean, we're going to do that. I'm not sure if it's exactly the same trick. So how does the trick work?
Well, you basically add by hand a term that would be non-local in 4 dimensions, but kind of becomes a local potential on the circle at finite temperature. This goes under the name of double trace stabilization or whatever you want to call it.
I see.
It's been studied since the 80s, but
I'm not familiar with this.
so this is a deformation of the theory. It's no longer Yang-Mills, but Yang-Mills plus something that explicitly prevents it from ever deconfining.
Even if you consider very small.
Yes,
cycle.
and go to arbitrarily small circles and say, in fact, it becomes perturbative. So that would be a setting in which one could, in principle, follow this.
Right. Yeah, that's very interesting. So we're going to do a very similar thing, but by going to the cylinder rather than the. So this would be like if you do a force partition function, you run trouble. But I hadn't thought about it. So this would be higher dimensions than D, like 3 or 4, like we're going to the 5th dimension, for example. But
No. You could take 4D theory on a standard thermal circle, except that you on top of that add some extra terms to the Lagrangian, which are localized in the circle direction.
Okay. See. Yeah, no, I wasn't aware of that. No, that's cool. So yeah, so that would be good. What right. Thanks. Okay, so there's any more comments? So so this one's not great, and there's in the using the most vanilla way. And then the other observable would be this one, which is the asymmetric. And we found that at low energies, we have an effective strength delay description. This was this one here. Now the question is at energies much higher than 1/ls, asymptotic freedom should kick in, and this high energy is sort of boosting the Goldstone to very high energies, and then this process should be controlled by asymptotic freedom. So here there are some expectations of what happened, mostly by Dubovsky, and the idea is that most likely this should emphasize this description. These expectations are mostly qualitative, and then the idea is that these constants become some globals, some definitely new, so gluons that are shooting off against each other. So at very high energies, each of these deformations becomes some gluon, and then in the UV, you just need to compute the scattering of some highly boosted gluons. But this becomes a UV process, and there's some expectations of what this asymmetry should look like. In particular, there's claims that it should be a linear phase shift, but with a different coefficient here. Now, the issues of these claims are they're not sharp, so they're qualitative expectations, and the reason they cannot be made sharp is because there's some IR string on top of the whole process. So this is some energy process on a very long string, which is a very IR process. So what one would first have to have some sort of factorization theorem where you have some UV process separated from some IR process, but such theorems don't exist so far. So at best, these expectations are just qualitative, and the issue is that we cannot just compute this thing from asymptotic freedom because it's not a bulk process. It's something that happens on the worksheet. Okay, so the issue is that so far it's hard to make this one precise. So instead, what we're going to
expect even for wildest imagination such a factorization theorem to exist.
do I expect?
Yeah.
I can convey that Dubovsky expects it.
But the usual intuition, the Yorkian intuition for why such a thing might work is because if you go to a very boosted frame and the target, a proton or whatever you're scattering from is very contracted, and so everything is very slow. Here it won't work because if you do a boost along the strings, the strings still remain the string.
Yeah.
So it's not, anyway.
Yeah. I find it very, it's.
Yeah, I asked for your opinion.
Yeah, okay, I can well, but I'm being recorded, so maybe I won't say. No, it's I can just say it's challenging, and indeed they can shoot past each other, and then there's so the picture is that there's some zigzag picture where they shoot each other against each other, past each other, but there's still like some they become this, and then this part over here ends up like showering into, so this becomes again, so one of them is going this way, one of them is going that way, and then this showers into a string that's very excited, and the two guys going back again. So indeed, like there's a lot of things going on that are very IR. So it looks hard to believe that there really is some like sharp UV factorization between like UV and IR. But what's going on? All I can say is that this is not the observable we're looking at,
Okay.
because it's not the sharpest. No. With that, I'll move on. So the observable that we're looking at that has the best of both worlds is nothing fancy. It's just the Polyakov loop correlator. So loop. And this is essentially the main observable that's actually used in lattice simulations. It's nothing strange. And it's the following. So we have correlator is in Wilson loop in the fundamental wrapping. So okay, my theory is again on R S1 with some rated R times RD minus 1. So the same setup as there. And now what I do is I wind two Wilson lines in the fundamental position tau. And in the end, the fundamental from position 0 around the length R. So it's basically the following picture. You have some cylinder with some radius R, so length R. And then I wrap a Wilson line in the fundamental here, comes up, another one in the anti-fundamental that goes down, and they're separated by some distance tau, which I think of as Euclidean time flowing that way. Okay, so it's, from a space-time perspective, it's just a two-point function of these non-contractible Wilson loops separated by some distance tau. And I'm going to be working, and they're specified with two parameters, tau and r. And I'm going to be working at fixed r. I will only play with tau, and I'll keep r bigger than the Hagedorn and the Hagedorn radius over here, so that I remain in the. So I'll be my theory will have a large enough radius so that I'm at low enough temperature, so in the confined phase. And then I will only play with this separation over here. Now, the first thing we need is a map to the worldsheet. We're a large N, so the main worldsheet that contributes is a cylinder going from one to the other. So the Wilson line becomes a boundary condition, a boundary for your string, and the main worldsheet that contributes is just a cylinder from one to the other. You know, where I find an end or one of our end directions, there would be things like this, like some handles on it. But I've been working at the strict large N limit where I can just focus on the cylinder. Okay, so the statement is that this so yeah, the statement is that this thing becomes the cylinder partition function of our dual string field that depends on tau and r. And that's important, as it was asked before, that the theory is not conformal, so it does not actually depend on tau over r, which is the usual statement in string theory or in conformal in CFT. It actually depends on tau and r, namely tau over ls and r over ls. So it depends on the two parameters. But the same description that we usually use for it, in the sense that there's two channels that you can look at this at. So there's an open string channel where my string is attached from one of the probe quarks to the other one, and I have a thermal trace with some temperature R or some beta R. Or there's another channel where I have a closed string that's winding in this direction, such as like we have there, that shoots between one boundary to the other boundary. So it's still true that we have the two quantizations. It's just that now they're no longer related by modular term. That's the main new ingredient. Really like the other chart. Good. So now, right, so we have this observable that maps well between the space-time and the worldsheet. Now the question is, what happens in the UV? So we're going to go to high energy, so tau much smaller than Ls. And then at some point when the separation is small enough, asymptotic freedom should kick in, and we should be able to complete this thing in using perturbation theory in the space-time picture. So then the statement is that we have the two Wilson lines that look like this. We have one going up, one going down, and then there's a diagrammatic expansion follows. And you start, so now you're in the close to the UV theory, so you can just add Feynman diagrams, and the various things we have are gluons being exchanged between one another. So first there's all the ladder diagrams coming in, and then eventually there's also other corrections, like self-energy corrections of the gluon and things like this, and so on and so forth. Okay, so this is the 2-point function at high energies. Looks like this expansion. And then the point is that at high energies, when tau is much smaller than Ls, you're looking for the leading divergence of this perturbative expansion, and you see that it comes from these diagrams over here. These ones are suppressed by they're suppressed in an expansion as tau goes to 0. So these diagrams over here exponentiate. It's a bit non-trivial because you need to be careful with the color factors, but they come out right. This is an old computation that was done in the single literature, and it comes so they just essentially exponentiate, which is what you would expect. They exponentiate to this diagram. So there's a web, and then there will be the next one with the self-energy correction and so on. And at high energy, since each of these is proportional to one of the like 2 coupling squared, is 2 coupling to the 4th, and so on. But at high energy, the 2 coupling goes to 0. Then the higher orders are suppressed, and they don't give the leading divergence. The leading result, that goes to 0, comes from this diagram to exponentiate. Now, what is this? It's nothing special. You take this as when you will be familiar with. Take this diagram and you do the Fourier transform so that it goes to position space. This is nothing but the Coulomb potential. So it looks like. So this becomes energy to the. Let me make sure I have the factors right. But it's energy to R. So minus R, and then some potential, which is a Coulomb potential. This Coulomb potential, can people see here probably? This Coulomb potential is the following. It's some factors come from the beta function. 1 over tau log tau. Double dot is equals to 4. So Coulomb potential leading order will be 1 over tau, which is just coupling squared, and then we use the one loop running of that coupling, which is the leading divergence is 1 over tau log tau with this fixed coefficient. And the scale of this log is fixed by the subleading corrections in terms of lambda means. And then in D equals 3, instead there's explicit coupling, which has now dimensions 4 pi log tau, and again the scale is fixed by the subleading corrections. Okay. So the statement is that this 2-point function at short distances is controlled, has this behavior, G minus R times the Coulomb potential. The Coulomb potential is the usual one, equals 3 and 4 and 4. Now, what I need to explain is that by doing this limit, that goes from some finite scale to much smaller than LS, we haven't exited the space that we were interested in, and we still can call this the high energy of the same string that we were talking about. And the main evidence for this comes by looking at the ground state energy of the open string. So now I look at the limit as R goes to infinity. This projects to the ground state of this open string, and I can plot the ground state energy similar like to this plot. But now the ground state energy of the open string as the function of tau. So now I have strings separated by 2 forks or non-dynamical forks, and I plot this again. It goes to a linear term, which is what you expect by the confining potential here. But then as you start coming down, this is using relative simulations, it comes down here where it becomes the Coulomb potential. So we go from linear equal to tau to 1 over tau. That wasn't the equals to 4. Okay. So, but the important point is that there's no finite tau value where there is some phase transition. This thing is completely smooth. So as opposed to this, where at some finite value of R, we had some sharp transition that should like bring us to a different phase or a different strength theory. Here we have some smooth behavior. Therefore, we expect that even by the time you go to a very short distances, where asymptotic freedom kicks in, you haven't actually left the confining phase, and you can still talk about the energy behavior of this Okay.
Does the
So-
energy become negative?
I'm sorry.
Does the energy become negative?
Yeah, energy can become negative. That's right. It's just attractive, but it's not complex. That's yeah. Any more questions? Okay.
If
So
lattice simulations for open string didn't exist, then would this be your expectation?
these exist. This is in practice. Yeah.
Right, but if it didn't exist,
But
then
if it
like
did,
I mean, this seems like maybe a natural expectation, but
Yeah. So I don't know what comes first, but yeah, there's expectation from holography. So some question that you could have asked is, well, lattice simulations are always at finite NC. Well, why do you trust that there's nothing going wrong as NC goes to infinity? And then the only answer is from holographic confining models like the Klebanov-Strassler, where the picture is that you have your CFT boundary and your ADS and the boundary. So yes, the boundary of ADS. And then what you have is the Wilson loops sitting somewhere here, and you have a string that probes the both. And then as you move one between the other, there's only one saddle that just probes the short distance here, or it probes all the way down where it has the linear potential from one another. And in this case, I mean, it depends on the model you have. It's like by the time you start calling in holographic models, then there's many things that can go wrong. But there are several where you don't, or at least some where there's no fit condition as you change. So would it have been my expectation? I don't know. But yeah, but this is certainly what we expect. Any more questions? Great. So okay. So we have, to recap, we have this fully coupled correlator. We know its user behavior driven by that. And now we've equated this to the cylinder partition function. So now we can forget where this came from. We just have some 2D theory, which is the worldsheet function of our string. And we look at the cylinder partition function. And as long as R is large enough and I take tau very small, it should have this behavior. So as tau goes to 0, it should go to e to the minus R dc of tau. Well, let's see by that. So then my question is, what does this teach us about the distributive string duals? What does it teach us about the worksheet? And I'll start. Should I finish on time, like sharply, or you guys go over? No,
It's fun to go
it
over.
depends on time. Okay, how much I can rush. Okay, so good. So now we're going to look for consequences of this fact and see what we can learn. And we'll learn, we'll do two main exercises. So one will be about the closed string spectrum, so reading it this way. And the other one will be about looking locally around a boundary, what happens here. Related to Julia's question of once you have a boundary and in terms of scattering, what does it mean for the Gaussians to scatter against the boundary? But let's not get ahead of ourselves. First will be consequences on the spectrum. So what do we do? Well, we read this similar partition function in that direction as the following. So z of cylinder is basically a state. The Wilson line creates some state, some boundary for some closed string state, e to the minus tau and Hamiltonian of the closed strings, the closed string, and then the dual state over here. And then we insert the complete basis of states, and we write it this way. We have an integral over the energy from 0 to infinity of some spectral density weighted by the Wilson line, complete energy, e to the minus tau. So this thing is just, we've inserted a complete basis of states, and it's a sum over all the closed string states of the coupling of a closed string state to the Wilson line, the boundary state, times a delta function or the energy of the state. Okay. So we have, yeah, basically we've inserted a complete basis of closed string states. So this thing sums over the Hilbert space of closed strings. And if we see that it is just a way to write it as a Laplace transform. So we have the spectral density, which comes the density of states weighted by their coupling to the Wilson line. And now the statement is okay. So we've written the partition function in this way. What do we learn by looking at the limit of tau going to 0? So as tau goes to 0, this factor goes away, and then we have an integral all the way to infinity, and this is controlled by the asymptotic tail of the spectral density. So what we're going to learn is the limit. Basically, what you do is you do a Hardy trick. You plot this behavior as tau goes to 0, and then you learn about the asymptotic behavior of the spectral density. So we learn that rho of E as E goes to infinity. Now there's one subtlety that I won't go too much on, but that's if I were to look at this weights the spectral density, this weights the string states by their energy. And their energy is not just their mass, but it's also their kinetic energy in the transverse direction. And that's not very interesting. So the statement is that this E of a string, or something, this is a closed string winding some radius R, so it's an energy that depends on R, and this is given by some, that's the usual expression relation, it's some mass of the string function of R plus the kinetic energy in the transverse direction. So we don't want to wait by this. What you need to do, instead of using this thing, use some Bessel functions, the propagators of a string, just of a particle in lower dimensions. And then what you're doing is not an inverse Laplace transform of that, but you just invert the one with the Bessel function. This is just a technical complication, but the statement is that we can extract the spectral density not as a function of their energy, but as a function of their invariant mass when we have an actual string at rest. All it does is just you do some additional Fourier transform in the transverse directions. That's all you do. I can say more details later, in interest of time. And then you do these inverse transforms, and you find the asymptotic density of states in terms of their mass. And they are the following. So in 4D, the expectation is exponential of the square root. The square root with some factor that ultimately comes from the beta function, 24 over 11 Rn, where n is the mass of the string, and log m. And in d equals 3, you find m to a power, which is given lambda r divided by 4 pi minus 2. And this is d equals 4. And this is d equals 3. Okay, so the exercise was have the cylinder partition function. We have its short distance behavior, and that gives us the asymptotic density of states in terms of the mass of the states. And we see these two behaviors, which at first may not be very illuminating. We have an exponential of square root of n and just a power law. Now they become surprising when you compare it to your expectation. And by expectation, I mean the expectation of the density of closed string states. So unfortunately, the project's here. But if I look at the density of states, meaning the sum over these delta functions, but without the weighting to the coupling to the Wilson line, what you find, what you expect is that this density, rho without W as a function of the mass, you expect it to have a Hagedorn-like behavior. So e to the m divided by r hat, or times that Hagedorn. And this is because when we look at the cylinder, when we look at the torus partition function, we found, unfortunately deleted it, we found a Hagedorn transition. And this from the closed string picture comes from the density, when the density of closed string states is too high, it overwhelms the Boltzmann factor, and then it triggers some phase transition. So this is what we expect for the density of states when you don't weight it by this coupling. But then by the time you turn on this coupling, you see that from an exponential linear in n, it goes to an exponential with square root of n, which is milder, or in d equals 3, much milder, which is just a power law. So the statement is that this coupling of the closed string state to the Wilson line must decay. So on average, the coupling of a closed string state to the Wilson line must decay as the energy as the mass goes to infinity, must decay linear with this, e to the minus mr, plus some corrections which leave this subliving growth. Okay, so what the main result so far is that if you have a theory of strings that you want them to be confining strings of a theory which is asymptotically free, their boundary states, which represent Wilson lines, must have a coupling. So the coupling between a closed string state and the boundary, the Wilson line, must decay exponentially with the mass of the closed string states. If you're looking, you have a Wilson line, if some string goes into the bulk, this coupling must decay when the string is very, very excited. Now, you may not have an expectation of what this coupling should be in general. So I can say that if you look at critical bosonic strings with d equals to 26, the usual bosonic string, we can do an exercise for comparison, where you put a dp brane, and then you consider the exchange of a closed string with another dp brane, separated by some separation tau, and you can just compute the cylinder partition function. It's a standard exercise, and you can extract what this coupling between a closed string and a dp brane is. So from a Worldsheet perspective, it's just the overlap of the boundary state, which is on the boundary state, and then your oscillator. So and tilde, which is your closed string mode, and the closed string state. And this looks like follows. It's different factors, but it's e to the I x k transverse. So k transverse is the momentum of this node. X is the position of the dp brane. It's just some usual phase. And then you have some factors of alpha prime, which is the usual thing. 6 minus p over 2, where p is the p of the brane. Anyways, this is not too important. The point is that you see there's no dependence on n or n tilde, which is the number of oscillators on your closed string mode. So essentially, the energy or the mass of your string is proportional to this n, and squared is proportional to n, and there's no n dependence on this thing over here. So the statement is that this analogous coupling between the closed string and the boundary, which is the dp brane, actually does not decay with energy at all. It's constant. Okay. So this is very surprising from this perspective, but because a confining string predicts that this coupling must decay. Now, this is directly related to the existence of a tachyon in this separation. So an open string tachyon. So the analog of this picture is looking at the ground state energy of an open string attached to the two dp branes separated by the distance tau. And you start bringing it down, you find something that's much similar to what happened in the closed string case. You find a tachyon and also a Hagedorn transition in that case. So the statement is that in order to avoid that phase transition in the confining in a asymptotically free confining gauge theory, what you need is that this coupling, so the coupling of the closed string to the boundary, must damp this Hagedorn growth and kill the open string tachyon. That's ultimately the word what is meant. So this is one of the main consequences. Any questions, please?
I probably missed it, but can you say a little bit about the torus came about that you use?
Yeah, sorry. So there was this picture. So I was comparing two spectral densities. There's one which appears in the cylinder and one which appears in the torus. And I'm looking at the torus partition function. This thing is trace of e to the minus r. Well, it depends on what I call them. We call it beta. So there's one cycle. So this will be beta. This thing will be r. R I'm living implicit, and now the thermal time is theta h of the closed strings. And this is a trace on the Hilbert space of closed string states. Now, what is this? What we use is that this thing is not a trace. It's a propagation from one boundary to another of e to the minus tau h cl w. Okay, so it's the same factor inside, the same propagation of the same theory, but here you send it with some states, here you don't. Here it is a third trace. So what happens is that this thing can also be written in this way, like as an integral of a density of this factor, but now it's not a density weighted by this coupling, it's one where you delete this. That's what I was calling rho. And that's the one that we expect it goes like e to the m, because we know that this one, as beta gets small enough, hits a higher restriction. Whereas this one does not. So that's basically the tool. Introducing a boundary has allowed us to go all the way to that. Yes.
Is this difference between like, so the D equals 26 was an example, and the WM overlap that you wrote down is related to the fact that the worksheet theory is conformal in that case, whereas over there, it's
That's a good question. So you're asking if half a theory is non-conformal, we'll find something else. So yeah, this was asked by me, was asked to me like a couple of weeks ago. I hadn't thought about it. And then we looked at one example, which was a massive, so CFT, which is a massive boson, massive free boson. And you can compute again the overlap with the Dirichlet boundary condition, and you find the same result. So some things depend on a scale, but you still find a constant that's not dependent on the mass. So it is not directly related to that, but yeah, it is an open question, at least to me. Can you mimic some example or look up some CFT or some non-CFT, which will obtain some coupling to a boundary state that decays with energy? Yeah, thanks. Any more questions? So I have a question for the organizer. When should I stop? I can very, very quickly say the other one, or I can do it very slowly, or I can just not say it.
Maybe you can quickly
I can
talk
say
about the other channel and then.
So, yeah, so I'll quickly say the other result, which is similar, it's related to that, but with a different flavor, which is that we'll study. It's gonna be messy, but we want to ask. Okay, so we're doing this party trick on the string density states. We've extracted this decay of the coupling, and now the question is, what does that mean microscopically for the dynamics on the worksheet? So the second thing will be worksheet dynamics, and the second one is, well, while the bulk action was described by the S matrix, it was these two ripples coming in and coming out. Like the picture that I had. The boundary condition, so this was the S matrix. The boundary condition is described by the following. We have a small Goldstone coming in at some momentum P, and then we have the same Goldstone coming out, momentum P, and this is my boundary Wilson loop. So this thing depends on another scattering process. It's the one-to-one process against the boundary, and it's what's called the R matrix or reflection matrix. It does not. It only depends on P because then it's broken Lorentz invariant. It doesn't depend on P squared. It depends on P. Okay. And so you have the worksheet by worksheet dynamics. I mean the scattering of Goldstones. And in principle, these are proxies for the action. So knowing R and S would get us a long way. Although R and S for all energies would get us a long way to knowing the full worksheet action. So the question is, what does asymptotic freedom or particular light result imply for these two objects? And so for that, what you need is a clean map between R and S matrices to the cylinder partition function. So we have scattering data, and the question is how is this related to the cylinder partition function? Cylinder partition function. And this in general is not known. So you're trying to relate, so this is data in infinite spacetimes, or at least that you have a Fock space. And this is something that's finite. So this depends on tau and r, which are both finite. and you're trying to relate infinite scattering data to finite volume data. And the relation between this is in general not known. There's a formula, a bit obscure, called D and B, after Dashon and Bernstein from 1969, which claims to provide some formal expression that relates the two, in general, like S matrices and rotation functions. But we tried playing with that, and it's very obscure because like there's various, like by the time you start plugging like 3 to 3 the amplitudes, you find divergences that don't seem to like make sense. So I would say that the theory relating these two things is still underdeveloped in general, but in integrability you can do a lot better because there is the thermodynamic deterrence that TPA thanks to homologic law. So the statement is that in order to answer this question of what asymptotic freedom implies for these two guys, so far you can only do it within integrability. So the toy model, what we do is we assume integrability and see what that gives. And that's of course just a toy model to see what things work. But it's not. We're not expecting that this. I mean, we know that these two things should not actually be integrable in the full Yang-Mills worksheet. So then, but then still as a toy model, you go through, you write the TPA ansatz, and then I'm going to spare you all the details. But what TPA does is it gives you this relation. You input these two things, and in that case, it's enough to do the 2 to 2, the 1 to 1 process that predicts. That's enough to get everything. Then you have the cylinder prediction function, and you use the fact that a star goes to 0. It's given by this Coulomb potential. Then you invoke the fact that TPA uses something called the time delay or Wigner time delay, which is it's 1 over I of S star ds. If I define the derivative in P. This particular combination is the only way that S enters the game. And the statement is that this time delay is actually must actually be positive by causality. So this is the statement that if I'm scattering 2 goldstones, it may come a bit delayed. So they come on the light tone. These are light tones, and it's coming in, the other is coming out, and it might come a bit delayed with respect to the trajectory that it has. This delay is this delta p, and it has to be positive if my theory is steps. So there was some debate as to whether this is positive only up to the uncertainty principle, because in order to talk about wave packets and trajectories, you need to be careful about that. But we managed to show that this is actually positive at all energies, just from an analyticity and unitarity of the S matrix. So at least into D for massless scattering, the time delay is strictly positive at all energies, and then we can use this into the TPA equations to obtain some inequalities for R and S. And we don't need to assume any S, we just use the fact that it has to be a causal interaction. And then by the time you go through the whole argument, you find that the R matrix as a function P must the R of IP must decay over. So this is the result in equals to 3. It's quite simpler. In 40, if you went to similar steps, we haven't actually done it. But this already highlights the point that this is the probability for the boundary. So if there's an IP, you've done a weak rotation. So you're looking at the probability for the boundary to create 2 goldstones coming in. So this is part of your excited closed string state. And then you see that this probability, as P goes to infinity, must be bounded by 1 over 2P. So in particular, it must decay. So we're seeing just from another completely different perspective with integrability, or you name it. But we've obtained that again, the coupling in some way of the Wilson line to closed string states, in particular excited closed string states, because they have a high energy, must also decay. And you can again compare this thing to what you get in this configuration. So the scattering of a goldstone of a critical string out of the Dirichlet boundary condition, and you find that the R matrix, I'm sorry, I missed an absolute value squared here. You find that the R matrix with absolute value squared is just equals to 1 in the critical Botonic string. So the statement is again that in critical Botonic string, with Dirichlet boundary conditions, this coupling is not damped at all. Whereas here, within integrability at least, it is also damped. We expect that even beyond integrability, once the methods are there, we also expect that these couplings in the reflection matrix matrices will decay with energy. But beyond that, it's still very much open. How do you obtain what are the microscopic what's happening microscopically for these Wilson lines to be so the coupling to these Wilson lines to be so that. And with that is pretty much where we're at. Now we're studying various directions beyond this. So something we're doing is trying to study subleading corrections to this UV behavior. So I told you that the UV behavior of the two lines coming together came from these diagrams, so the result perturbative. But we expect that at some point there will be non-perturbative corrections also coming in. And for that, what we're doing is we're studying this fusion of Wilson lines in terms of the theory of defect fusion. So there's in CFT, we have under controlled an OP of defects. So the I on the J is given by some direct sum of defects DC with an effective action on top of it. We can tell you more later if you're interested in. This work by Zohar, Ifan, Kraftchuk, and many collaborators. And this is within CFT. But we expect that by the time you turn on the scale, many of these things remain in form, but they receive perturbative and non-perturbative corrections. This is a way to classify, much like people do in local operators. This is a way that will hopefully classify the various corrections, and we're working through what the subliving terms will look like. So yeah, happy to tell you more about this, and then we also have some more phenomenological applications for this. And with that, thank you, and sorry for doing it.
The time delay here is finite. You don't have any problem.
Sorry, couldn't hear that.
The time delay is finite.
Time delay is finite.
Have any problem?
Yeah. So here, like the S matrix is defined everywhere. And so you could ask the same question for the S matrix directly. And there are no, so yes, you have massless particles coming into D, coming from very far away, but there's no IR divergences because the states, so you can have many particles coming in this direction, but there are no interactions between left moving, there's no interaction between them. There's only interaction by the time they hit the right moving ones, and that's why it's well defined to take all these states coming from. And you can take multi-particle states and they're distinguishable. So it's basically by the absence of like moving interaction. It's a special property of 2D and in particular of these cells.
And that inequality implies the one for the R.
So this inequality, yeah. So you need this and the fact that x goes to 0, yeah, and z goes like the e to the minus r is equivalent potential. So you need both. So there's one first step that's the inequality. So this is a causality bound, and then this is something that we like to call that there's causality bounds on thermodynamics. The SPDA writes for you the cylinder partition function, and you find using these, you find an inequality between the cylinder partition function and some integral of r. And then using that the cylinder partition function behaves like this, that's how you read off. So basically the Coulomb potential has this lambda, and that's how lambda comes in. And then you massage this expression, and you get this in the bottom. Those are the two steps. Thanks.
Any other questions? All right, let's thank John again.
Thank you.